So what I wanted to do today is begin by talking about set partitions. So last couple of classes, we talked about partitions, but these were partitions of numbers, right? So far our partition has been like 8 equals 3 plus 3 plus 2. That's what a partition was to us in the last couple of classes. And today I want to talk about set partitions, which is not going to be a partition of a number, but it's going to be a partition of a set. So, and it is what you probably think it is. So we're partitioning a set into pieces. So a set partition of a set S is a collection pi b1 up to bk of non-empty subsets, which we're going to call blocks, such that S is the disjoint union of those blocks. Again, these little boxes means the joint union, so this means that S is the union of these guys, and these guys are pairwise disjoint. So Bi intersect Bj is empty for pi different from j. Okay. So that's set partition, and we're going to let, realizing that this is not the best notation, but it's done. So capital Bn is going to be the number of set partitions of the set of n elements, and capital S of nk is going to be the number of set partitions of n with k blocks. Okay. So this is similar to several things we've done in the past, and these are called Bell numbers, the Bn's, and these are called Stirling numbers of the second kind. Okay? I'll remind you a little bit later in class today what the Stirling numbers of the first kind were. We saw them already, and these are going to be the Stirling numbers of the second kind. Okay? And so we want to play the same game that we've played with several different things that look like this. Okay? So I mean, let me ask you, what should we do now? That's the definition. So what should we do? Formula, generating function, recurrence, all these things, right? So I think the easiest is the recursion, because we even have this kind of technique where we always do things like this. So, okay, if we look at a partition of 1 up to n into k sets, and we just pay attention to where n is. Okay? In other words, imagine that you have one of n minus 1. You have a partition of 1 up to n minus 1. And now you want to add the number n. Okay? So, where do you add it? Well, we'll make a box and we're just going to prove it, and then we'll see what the answer is. So we're going to just make such a partition. And when I say such a partition, I mean a partition of the set from 1 up to n into k parts. We can do one of two things. We could take a partition of the set from 1 up to n minus 1 and then just add n alone on its own block. So add a new block n to a partition of n minus 1 into how many blocks? Well, if I want the new partition to have k blocks, then I need this one to have k minus 1 blocks, because I'm trying to add a new block, right? Okay, so how many such partitions are there? Well, this many. Right. If it's not like this, it's because I'm going to add n to a block that already existed. Add n to an existing block of a partition of n minus 1 into how many blocks? Well, if I want my new partition to have k blocks, then this one should also have k blocks, and I'm just going to add n to one of the blocks. Okay? So how many ways are there of doing this? Well, I can take any partition of the set of n minus 1 elements into k blocks, and then how many ways are there to add the number n to an existing block? You either add it to the first block, or you add it to the second block, or to the kth block. There's k options. So you get this. Okay. So it's kind of the same argument that we keep doing, and now we get this recursion. Okay. So that's the proof, and this gives us a recursive method of computing all of these guys. Okay. And let me write a couple of corollaries of this. Which is the next thing that you guys suggested, the generating functions. Okay. So for example, let's write this generating function. So what am I doing here? I'm fixing the number of blocks k, and then I'm looking over all possible values of n. Okay. Where should I start my summation here? Well, if I want to be able to partition a set of n elements into k blocks, and the blocks are supposed to be non-empty, then I should have at least k things in my set, which is why I'm going to start with k. And so then this is the usual way that we write a generating function, and it turns out when you do it, the answer is this: x to the k over 1 minus x, 1 minus 2x, dot, 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 1 minus kx. Okay. How do you prove this? Well, you could go for a clever proof, or you could go for a brainless proof. And I'm just going to mumble a little bit about the brainless proof, which is that you can just use induction. And it works. And maybe, because we've done similar proofs like this, maybe I won't do it, and I'll just leave it to you as an exercise to think about how, if you have this statement for a particular value of k, then you have it for k plus 1 using the recurrence. But I just wanted to write down the formula for you. And later we're going to talk about more conceptual ways of understanding this. But I also wanted to write a different formula, which looks like this. Okay? And I've mentioned a little bit, not a lot, how whenever you have a sequence, there's kind of two main kinds of generating functions that we use. Sometimes we use this kind, which is not called an ordinary generating function, and sometimes we use this kind, which is called an exponential generating function, where you always put an n factorial under x to the n. Okay? And so, I mean, this is a different generating function, so you get a different answer, and the answer looks like this. Okay. And again, how do you prove this? Well, you could try to be smart, or you could just try to be brainless. And again, if you want to do it brainlessly, it works recursively it works inductively using the recursion. Okay? The reason that I'm not doing these things kind of inductively is, first of all, because it's boring and I'll put you to sleep. But second of all, because actually I want us to get to the point where we just look at the problem. If we think about it enough, then we see that this is the answer. Okay? And we'll get to that point in this class where you'll just look at this formula and say, of course it's this. So I hope that's exciting to you, but maybe it seems like a very distant thing, but it's not that distant actually. We're going to get to a point where you just kind of understand why these formulas are true by just looking at them. We need to just develop a little bit of machinery for that. Okay? So, okay, for now we're just going to say proof, induct, or wait. Both work. Well, wait, but you have to come to class when we do it, otherwise it doesn't work. Okay. But yeah, so those are nice recursions for, those are nice formulas for the generating functions for Stirling numbers. Actually, you might also say, well, you know, if you have a sequence of two entries, why don't you use two variables? Okay. So I could have done, for example, the sum over n and k of x to the n over n factorial and y to the k if I want. And actually, that's also a nice way of expressing this, and we will again see very easily why. We will see very easily what that is when you use a two-variable generating function. Okay. Now, I'm not even going to talk much about Bell numbers, because I feel like we kind of keep doing the same things over and over again, where I introduce a combinatorial problem and we more or less use similar techniques, and then we prove similar things. And you can do it for Bell numbers, and it also works. Okay? And so Bell numbers also have a recurrence. They also have a generating function you can write down. Also, given these things, you can write out explicit formulas, and these are things that by now you've learned how to do with a little bit of work. So I don't want to focus on that too much. I do want to show you a nice property of Stirling numbers. Let me erase this because we're not going to really talk about Bell numbers, but we are going to talk about Stirling numbers more. So here's a proposition. X to the n is equal to sum k equals 0 to n Stirling number n comma k times x minus 1, x minus 2 up to x minus k plus 1, I think. Yes. So this is a polynomial identity. Right? This is x to the n. This is the polynomial, and then this is some polynomial. And I'm claiming that when you multiply all of this out, you collect, all you get is x to the n. So again, there's several ways of proving this. Some of which are to kind of you could do it inductively. There are several things you could do, but again, when you have an identity like this, I hope that by now you have the instinct that you wanna give a combinatorial proof if possible. So how can we find a combinatorial proof of this? Well, there's a couple of things you could do. One is you could say, okay, these are polynomials in x, so let me just compare coefficients. And you could just think about what happens when you multiply this out. It's going to be ugly, you can imagine. It's going to be a big expression. You multiply all of these things out, you collect coefficients, and you show that the coefficients are equal to this. That'll be a combination of some kind of slightly nasty algebra and some cleverness, some combinatorics. We're going to do something nicer, which is that we are just going to assume that x is an integer. X is a positive integer. And we're going to prove it in that case. And I claim that that is sufficient. It suffices to prove it when x is a natural number. Why is that? Because if you assume that this equality is true for x equals 1, for x equals 2, for x equals 3, for x equals 4, etc., then if you consider the polynomial this minus this, that polynomial has roots at 1, at 2, at 3, at 4, etc. It's a polynomial that has infinitely many roots. There's not that many polynomials that have infinitely many roots. The only one is the identity polynomial 0. Right? If you're not 0, then you have a well-defined degree, and that's how many roots you have. You can't have roots at 1, 2, 3, etc. Okay. So that's a very nice combinatorial trick to prove combinatorial identities. I mean, we're relying on algebra to show that it's enough to do it for the natural numbers, and in that case, these things all have combinatorial interpretations. And so that's what we're going to do. Yep.
Sorry, is that identity up there, is that supposed to be parentheses around like k plus 1?
No.
No? So I'm the dot dot dot, how is that going, I guess?
So you go x minus 1, x minus 2, x minus 3 until x minus k minus 1.
Oh, yeah. Oh, okay.
Which is some...
Yeah.
I guess...
0.
Yeah, maybe...
K factorial.
Maybe k equals 0 is a problem here. Let's do the proof, and let's figure out what to do with that k as we prove it. Because it might be that k... Actually, here's the answer. What is S of n comma 0? You're trying to make a partition of a set of n elements into 0 parts. And you cannot do that. So then this doesn't really make sense to put k equals 0. We should probably just start at k equals 1. And if we start at k equals 1, then this makes sense. Good point, thank you. Okay, so well, what's x to the n? That's a combinatorial problem that we study a lot. I'm gonna phrase it like this: x to the n is the number of ways of putting balls 1, 2, up to n into boxes 1, 2, up to x. Right? Because for each ball, you have x boxes that you can put it in. So the number of ways of doing it is x times x times x, n times. Okay. So that's what the left-hand side counts. And now I want to show that this also counts the same thing. Okay? And so this is one way of counting this, but another way to count this, a box here. I'm going to run out of space, so I'm going to make room over here. So we're going to try to solve that balls into boxes problem in a different way and show that the answer is in the right-hand side. So another way of counting this is going to be the following. Let's assume that we use exactly k of the boxes, k of the x boxes. Or let me say, and the number of ways to do this is the following. Okay, so you have to perform this task of putting these m balls into these x boxes, except that you're only allowed to use exactly k boxes. So what are the ways of doing this? Well, first, let's figure out which boxes I'm going to use. So out of the x boxes, I have to choose k of them, which I'm going to use. So x, this is the number of ways of deciding which boxes to use. Okay. And so now I have k boxes, I have n elements, and I want to put the n elements into my k boxes to make sure that I use all of them. So then, where am I going to get a Stirling number? It kind of proves itself because it says, okay, well, I have n elements, and I need to partition them into k groups, and that makes sense because I have to, put one group in each box. So S of n k ways of splitting my n balls into the k groups going into the k boxes. And then finally, so first I said, okay, out of the x boxes, I'm going to choose these k, I'm going to use them. Then I go to the balls and I kind of prearrange them. I say, okay, these m balls, I make them into k little groups, and now I have my k groups. These k groups have to go into the k boxes, and so I just have to choose who goes where. There's k factorial possibilities. So k factorial ways of choosing which group goes in which box. Okay, and so then for a fixed k, the answer is this. Put here as k factorial. Okay, this is the number of ways of doing it for a fixed k, but now I have to add over all the possible values of k. And k can be anything from one box to n boxes. So this is the number of ways of doing the same task. And x choose k times k factorial is this. And so this is my proof. Okay. So I guess you'll agree that this is a lot nicer than trying to multiply this out and try to compare coefficients. And this shows you this is a very powerful trick that whenever you have a combinatorial identity of polynomials, keep that trick in mind. Actually, this trick was very useful in one of the homework problems already. I think in homework 2. Okay. So this is a combinatorial identity, or you could also think of it as an algebraic identity of polynomials. And why is it that I want to show it to you? Well, because I want to compare it with something that we did earlier. But to do that, I have to remind you a little bit about Stirling numbers of the first kind. So remember that C of nk. We talked about these numbers, and they were, this was the number of permutations of n with k cycles. Okay. And we studied this, and we proved we computed the generating function for this, for a fixed n and variable k. We saw that this is equal to x times x plus 1 dot x plus n minus 1. So you might not remember this very vividly, but I hope it looks familiar. We proved this. And so this looks a little bit like that. It's kind of like the opposite. And I'm going to make it look even more like that by reminding you that the Stirling numbers of the first kind were lowercase s of nk, and they were just these numbers with this sign. Okay, and so you can just let's plug into here. I'm going to make a quick computation. Okay. I was going to omit it, but maybe I'll do it real quick. So if I plug into here, C of nk is equal to minus 1 to the n minus k s of nk x to the k, right? This is this. Okay. Now let me try to merge these two guys. And the way I'm going to do that is I'm going to pull in minus 1 to the end. I'm going to pull it out of the summation. And this minus 1 to the k is going to combine with this to give me this. And actually, now let me take this minus 1 to the n and send it to this side and just change the sign of all of these terms. Okay, there's n minus sign, so I get minus x minus 1 up to minus x minus n plus 1. This guy disappears. Okay, so I'm just doing some algebraic manipulation, and now what I'm going to do is I'm just going to change minus x for x. And so what am I going to get? I'm going to get this. So here I just substituted minus x instead of x. I got this. So the reason that I wanted to show you that is because I want to put it next to this one. And I guess here I should also go from k equals 1 to n, because again, you cannot have permutations of n with 0 cycles. Okay? So this is combinatorics, but this is also algebra actually. These formulas look very similar to each other, right? And you see the first formula, or let me say it the other way. The second formula takes this polynomial and tells me how to express it in terms of x to the 1, x to the 2, x to the 3, etc. And this does the opposite. It starts with x to the 1, x to the 2, x to the 3, etc. And it tells me how to express it in terms of these polynomials. And I hope this reminds you of linear algebra. Really what we have here is just a change of bases between two bases of a vector space. So that's how I want to kind of reframe what I have here. So let me say note that a basis for the vector space of, let's say, real polynomials. So this as a vector space over R is, and kind of the standard basis that we use for polynomials is 1, x, x squared, x cubed, etc. So we might call this the first basis. Okay. So we know that this is a vector space of infinite dimension, countable dimension, and this is a basis. So what I claim is that we just produce a second basis. It also starts with 1, then x times x minus 1, then x times x minus 1 times x minus 2, etc. Okay. So I claim that this is also a basis. How can I prove it? Well, yeah.
So the degree of the maximum degree of each of these polynomials is like unique. So linear depends.
So you're already being more clever than I was gonna be. So Brian was saying it's because the leading degrees here increase 1, x squared, etc. Basically, what that means is that this guy can be expressed in terms of this one by a lower triangular matrix. But I want to say something even easier, which is that, look, here I'm showing how to express any x to the n as a combination of things in B2. So I can express everything in B1 in terms of the ones in B2, and therefore B2 has to be a basis, because if I can generate x to the n, I can generate anybody. Okay? So those are two perfectly valid proofs for why these two are bases. And so when I have that, then I can really frame this in terms of linear algebra. And I can say that the matrix if I make a square matrix, infinite matrix of all the s of n comma k's, then this is the transition matrix. When I want to go from basis B1 to basis B2. That's exactly what this says. Okay. And let's make this plural, because I can also consider the matrix of Stirling numbers of the first kind, and that's the transition matrix from B2 to B1. Okay. So this is supposed to be a plural sentence now, so are the transition matrices from B1 to B2 and from B2 to B1. Okay? And so this means that whatever we know about linear algebra, we could apply here. So for example, what do we know about the transition matrix from B1 to B2 and the transition matrix from B2 to B1. They have to be inverses of each other, right? This is almost by definition of being a transition matrix. So therefore, this matrix is the inverse of this matrix. Now, you might not be used to this because these are infinite matrices, right? These matrices go from n and k equals 0 to infinity. Okay, so these are matrices that, let's see which way should I point so you guys see it. So there's a corner here, right? And they have infinitely many rows, infinitely many columns. And so I have one infinite matrix and another infinite matrix. So what does it mean to be inverses? It means that when you multiply this one times this one as infinite matrices, you get the identity matrix that has only ones in the diagonal and 0 everywhere else. Okay. And so, for example, here's a corollary. What's this? What do I get when I sum this over all possible values of k? Where this is Stirling numbers of the second kind, and this is Stirling numbers of the first kind. Well, you think about what this should be equal to. Let's talk about what am I summing over here? What can k be? Well, for this to make sense, n should be bigger than k, bigger than or equal to k. And for this to make sense, k should be bigger than or equal to m. So that means that I get this from m to n. The other one terms are 0. What's this? Well, if you think about it from the matrix point of view, this is just the entry nm of the product matrix, and we know that that product is the identity. So that means that this thing is 1 if m is equal to n, and 0 if m is different from n. And so this gives me a completely algebraic proof of a completely combinatorial identity. I mean, these things really have combinatorial meanings. And I mean, this could be a homework problem, and I think that is not an easy homework problem, actually, to prove this combinatorially. But somehow, it seems like this is really this feels like a right approach to prove this. This really feels like a nice, consistent story that comes together to show something like this. But yes, I wanted to show you this so that you can see how Stirling numbers of the first kind and of the second kind are closely related to each other, because the definitions were very different. But this shows that really they're very closely related to each other. So are there any questions about Stirling numbers? Okay, so what I want to do for the rest of the hour is basically I'm going to try to, in the 30 minutes or maybe a little bit less that I have left, I'm going to try to put together everything that we've done in the class and summarize it in essentially one table. Okay, so that's why you see a table in front of you today. And what I want to try to illustrate is that not everything that we've done, but very, very much of what we've done fits together into one very simple framework, one very simple question, which is the question, how many ways are there to put n balls into n boxes? Okay. So that's what we're going to be talking about for the rest of today. It's just the seemingly very easy question of putting balls into boxes. Okay, and you could put subtitles to this, like putting it all together. Or a common title for what I'm going to discuss is Rota's 12-fold way. So it goes like this. So question, how many ways are there to put n balls into n boxes? Okay. Well, you might argue we already answered this question about 5 minutes ago, but actually, I want to show you that there's several natural meanings to this question. So the answer depends on how you're thinking about this. For example, can you tell the balls apart or not? Are the balls distinguishable? Yes or no? Are the boxes distinguishable? Okay. And the third question that I want to ask is, are you allowed to do it in any way you want, or so it's going to be a three-way question. Any arrangement, or do I have to use all the boxes, or do I have to put at most one ball in each box? Okay. And you might think that what I'm saying here is, do I have to use all boxes? This is kind of like saying that this is a surjective mapping from the balls to the boxes. You have to hit every box. And do I have to put at most one ball in each box? This is the question of whether your mapping of balls into boxes is injective or not. Okay? And so how many questions am I asking here today then? Well, there's two possibilities here, there's two possibilities here, and there's three possibilities here. 2 times 2 times 3 is 12, and so that's why I have a 12-fold way. Okay, there's 12 different questions that I'm asking in one. So I'm going to make a table here of all those questions. Okay, so in the columns I'm going to put any placement. Here's going to be at most one ball per box. And here's going to be that you have to use all boxes. Okay? And then here's my table is not quite big enough because I want to add two columns. So I have, let's see. So I have n balls, I have n boxes, and I want to know if they're distinguishable or not, okay? And so there's 4 possibilities for this. Right? Which is, make sure I do it in the same order as here, distinguishable, or distinguishable, indistinguishable, or like this, or like this. Okay? So I have a whole bunch of questions here. I'm going to answer all of them. And actually, if you happen to be watching on video and you're not in this room right now, then I would encourage you to press pause and actually try to answer all those 12 questions. We have developed all the necessary tools in this class to answer all of these 12 questions. So pause, try it out, and then, well, we're just going to have to do it live. Okay. Okay. So let's just do it. Maybe I'm going to number these. 1, 2, 3, 4, 5, 6. Hope you're answering some of these questions as I do all of this. And maybe, so while you keep thinking about some of these answers, maybe I want to draw some diagrams so that you see the differences between these 4 kinds of problems, because maybe you can tell that there's a difference, but let's make it a little bit more concrete. So for example, the problem we just talked about, I called the balls 1, 2, 3 up to n, and I called the boxes 1, 2, 3 up to x. So I can tell them apart. Okay? And so one way of putting, let's say, 4 balls into 3 boxes is to put ball 1 here, ball 2 here, ball 3 here, and ball 4 here. Okay? What would that look like here? Here you can tell the balls but not the boxes apart, so that means that the boxes are all identical. And so you could do it like this. And that's going to be the same as if you switch and put 3 in this box and 1 in this box. You can't tell the difference. Now this one, here the boxes are numbered. But the balls are not. You cannot tell them apart, and so I could put 1 ball here, and 2 balls here. And a different thing to do would be to put, let's say, 2 balls here and 1 ball here. Okay, that's different. But if I switch these two, I'm going to get the same thing. And then here, you have 3 boxes, they all look the same. And you have 4 balls, they all look the same, and so this is one solution. Okay. So these are the 4 kinds of problems that I'm considering here. So now let's try to answer them. And let me start with some that I already answered just now. So I think that we just did some of them. Which one did we just do? Well, we did one, right? We were talking about just putting n balls numbered into n boxes numbered, and we said, each ball has n possibilities for where it can go. And so you get n times m, etc. Okay? So we did that. We also did this one, where I'm forced to use all boxes. Because here, we said, okay, if I have to use all boxes, then let me take my n balls, split them into n groups, and then choose which group goes in which box. That's what we just did. So we just did that. The Stirling numbers come from there. And actually, we also did 2. Maybe a little bit in disguise. At most, 1 ball per box. Yeah.
For any placement, Are we also using all boxes?
Here you might miss some boxes. When I said, if I just put any ball at random into some box, then I might miss some boxes. And so that's why I have any placement and I have no guarantee that I achieve this or this. If I want to achieve one ball per box, then let's say, okay, well, where do I put ball 1? Well, there's n possibilities for where I put it. Where do I put ball 2? Anywhere except for where that went. Where do I put ball 3? Anywhere except for the 2 that I used, and so on. So I get this. Which also appeared in our previous proof. That's why I'm doing it very quickly. So we did those. Okay. Now let's talk about 9. How much is that one? So here I need to use all boxes. Okay, I have m balls, and so I do the same thing. I take my m balls, split them into m boxes, but now actually I don't need to figure out which group goes into which box because there's no difference. Okay, so it's the same thing except that I don't get the factorial. So I get that.
So I'm confused. You sort them into different groups, but then it doesn't matter which box you put them in. Is that what you said? Because that seems like the boxes being indistinguishable. I'm confused why it's not.
Yeah, actually, I'm realizing that I wrote this in a distinct order. So what I did just now was, yeah. So you're right. So I have these two switched. So I'm going to switch them now. Okay, so this is indistinguishable, distinguishable, and this is distinguishable, indistinguishable. Okay, so it's the opposite of what I did here. So here I don't know the names of the balls, or rather the balls have no names. And here the boxes have no names. But the balls do have names. So now it makes sense. Thank you. So I take my m balls, and they're numbered. So I have a set 1, 2, 3 up to n. I split it into m groups, and now those n groups already determine my placement because the balls don't have any names. Okay, that makes sense. So I get that. Now from that I can get 7 because what? What if I don't have to use all boxes? Okay, this is if I have to use all m boxes. What if I don't have to use them? Well, either I use m, or I only use m minus 1, or I use only one of them. And again, because the boxes are not labeled, I don't really have to decide which m minus 1 to use. It's all the same, right? They're all indistinguishable. So I get this answer. So it's just the sum of the Stirling numbers. I write it like this. All of the Stirling numbers as nk for k from 1 to n. Okay. What about this one? At most, 1 ball per box. And I cannot tell the boxes apart. So that means I have to take ball 1 and I put it in a box of its own. Then I take ball 2 and I put it in a box of its own. And I can't tell the boxes apart, so I'm just putting them into boxes. Okay. So how many ways are there of doing this? Well, just 1 if the balls fit, and 0 if they don't fit. In other words, if the number of boxes is greater than or equal to the number of balls, then the only way to do it is to put ball 1 in one box, ball 2 in another box, ball 3 in another box, etc. But if I don't have enough boxes for all the balls, then there's no way of doing it. Okay? So 7, 8, 9 are easy. Okay, now what about 12? So now I have n balls, and I have to put them into n groups, and I cannot tell apart the balls, and I cannot tell apart the groups. Okay? So split my n balls into n groups, but I can't tell anything apart. So what I'm doing, okay, so if I split our n indistinguishable balls into n indistinguishable groups, the only thing, yeah?
Sorry, if you, over here on number 2, so can you explain why it doesn't matter about m or n, which one's bigger?
So it's a very good point. So let's talk again about whether the balls fit or don't fit. If m is greater than or equal to n, then I guess you're happy with this. But if m is less than n, you're worried. And I guess I was careless, but I got away with it because if m is less than n, then m minus n is one of the factors here. Sorry, m minus m is one of the factors here. So this is equal to 0 by log, and the answer is 0. So thank you. It's just lucky that it works out that it's the right answer. Right. So for number 12, I have my n balls. I split them into groups, but you see, all I can tell is just how many balls are in each group, and I also don't know which group is which. Okay. And so really, what I'm doing is that I'm taking the number of balls n, and I'm just splitting it into numbers. Like this is 4 is 2 plus 1 plus 1. So this is just a partition of the number n into n parts. Not a set partition, but a number partition. And so the number of those is what we call P sub n of n. Okay? A partition of n into n parts. And similarly, if I don't have to use all boxes, then I get a partition of n into, at most, n parts. So we call this like this. So if I now do 10, which is into at most m indistinguishable groups, then I get partitions of n into at most n parts. And if I have at most one ball per box, then again this is a very boring problem, because the only way of doing it is to put one ball in a box, another ball in a box, another ball in a box, and either they fit or they don't fit. So I get the same answer as above. I get 1 or 0 according to whether they fit or don't. Okay? So we did, okay, so 11 is boring, 8 was boring, and 11 is boring. Okay? So now let's go to 5. So the boxes are different, the balls are the same. I have to put at most one ball per box, and I have to put m balls in there. So what do I have to do? Well, I have my m boxes 1, 2, 3 up to m, and I just have to decide out of those m, which n of them are going to contain a ball, and which ones are not. this. Okay, choose out of boxes 1 up to m, choose which end containable. And so that's m choose n. And to go back to your point, again, somewhat luckily this works out that if m is bigger than n, this is a positive number, and if m is less than n, then this is equal to 0. So that's fine in both cases. Okay. Maybe we'll go to 6 now. So now my boxes are different, and I'm allowed, but I have to use all of them. So if I put I balls into box I, the point again is that the balls are all the same, so the only thing that matters is how many I put in. So if I put AI balls into box I, then what do I get? I get a way of writing the number of balls as A1 plus dot 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 plus AM. And this is a composition. Composition of n into m parts. Okay. And so when you see basically, I delayed this until we had done every single one of these problems.
Which some AIs can be 0?
So no AIs could be 0 because I have to use all boxes.
Oh, 1, 6, sorry.
Right? So but we'll get to that in just a second. But in 6, I have to use all boxes, so all of these guys are positive. So this is an honest composition. We enumerated them, and we saw that they were given by n minus 1 choose m minus 1, right? Our proof was to say take 1 plus 1 plus 1 plus 1, and out of the n minus 1 pluses, choose n minus 1. Finally, 4. So 4 is kind of the same thing, except that as Brian was noticing, well, this is the case where you might have some empty boxes, so these AIs could be 0, and so in this case we get weak compositions. In case number 4, compositions into parts greater than or equal to 0. But again, we already computed what those are. And remember, our trick for this one was that if we added 1 to each one of these parts, then we got an honest composition of n plus m. So we got that the answer was n plus n minus 1 choose. Okay. And actually, we had a symbol for this, which was m multi-choose n. So it's equal to this. Okay. So I don't know how this makes you feel that we've spent a month counting and now it all fits into half of a board. But I guess one thing that means is that we've gotten good at this, and that all of these questions are at this point pretty easy. Now, of course, part of the point is not just writing down some symbols. I mean, if I showed you this the first day, well, okay, well, what does S of n m mean? What do all these things mean, like partition functions? The point is that now we know a lot about each one of these things. Okay. So it really could be said that we're getting pretty good at putting balls into boxes, okay? Which might seem like a modest goal, but I think it's a good goal, and I think you knew at the beginning of the class that putting balls into boxes is a difficult business sometimes. So I wanted to conclude with this quote that I like a lot. So this, one of the people that I learned combinatorics from was Giancarlo Rota, whose name I erased here. And when you took classes with him, everything was balls and boxes, and he kept going back to that, and he would give you these very, very difficult problems that were all about balls into boxes. And I wanted to read you this quote about combinatorics that he has. And I'm going to post this on the forum so that you can go back to it. I think it's a nice quote. So this is Giancarlo Rota from Mathematics, Philosophy, and Artificial Intelligence. So he says, combinatorics is an honest subject. No Adels, no sigma algebras. You count balls in a box, and you either have the right number or you don't. You get the feeling that the result you have discovered is forever because it's concrete. Other branches of mathematics are not so clear-cut. Functional analysis of infinite dimensional spaces is never fully convincing. You don't get a feeling of having done an honest day's work. Don't get the wrong idea. Combinatorics is not just putting balls into boxes. Counting finite sets can be a highbrow undertaking with sophisticated techniques. I should say, he was actually trained in functional analysis. It's not that he was just like saying analysts don't know what they're doing. He was trained in that, and then he actually switched to combinatorics. And he's kind of, according to a lot of people, he's one of the people that really kind of pushed combinatorics into the mainstream of mathematics by kind of helping organize the subject a little bit and showing the connections with a lot of things. But I like this quote a lot, and I would say that today we have essentially finished the elementary putting balls into boxes phase of this class, and then we're about to go into the highbrow undertaking of learning all the sophisticated techniques. So, I mean, even getting this far is tricky. We did a lot of tricky things, a lot of difficult things. And at this point, I think we basically have developed the main language, the main techniques, the main definitions. And from now on, we're just going to run with it and try to not only count, but also put a lot of structure to learn general techniques and things like this. And so I think you'll see the focus of the course change in that direction from now. Okay. I should tell you that also that I got this text from a website called What is Combinatorics? This is a question that I get very often in my life, and it's a very difficult question to answer. So Professor Igor Pak at UCLA made this incredible website where he gathers answers from dozens of different mathematicians about what is combinatorics. And so I'm going to post that on the course website. And one of your homework problems is going to be to write a little essay about one of those answers. It's going to be like maybe an unusual assignment for a math class, but I want to force you to read some of these things because I think they're interesting and they give you a little bit of a feeling for how combinatorialists think about what we do. Okay, so let's stop there and we'll continue.